Hello students, here we are going to discuss about Unit 3 of Computer Vision called Half Transform. Unit 3 notes can be available at the description part. You can download it. These are all the contents available in this unit. I grouped that contents in main four categories. First we talk about line deduction. Here we will see how the half transform helps us to deduct straight lines in an image. We also look at the foot of normal method, which is another way to represent and deduct the lines more effectively. Second one is line localization. After detecting that line, we need to accurately locate and fit them. This is where line fitting and ransack line fitting techniques come into play to improve the accuracy of results. Third, we will look at circular object detection. This part focuses on finding the center of the circles correctly using off transform. We will discuss the speed problem, which is a common issue with circular detection, and how we can also extend this into ellipse detection. And finally, we will explore some case study. We will apply these methods in real scenarios like human iris location, hole detection, etc. So, by the end of this session, you will have the clear idea about off transform and how it is used to practical image processing and object detection tasks. And in simple word, this unit covers how to identify the basic geometric structures present in an image. Now let's we go to these topics one by one. We need a special mechanism to identify these basic shapes. For this purpose, we are using the technique called off transform. This off transform convert the image into new space called parameter space, in which the calculation can be made and identify the basic shapes like lines and circles. Let's we see these topics one by one. First one is line detection. Line detection is one of the important process for computer vision. It can be used in many real-time applications. By using the edge detectors, we just identify what are the pixels available in the image. These edge pixel coordinates does not provide any information. We need to find any straight line present in the image. That's why we are going for line detection methods. The line can be represented in many ways. One is slope intercept form, another one is point slope form, 2-point form, general form, and normal polar form. So this polar form can be used in off transform because some other methods may not be fit for all situations. I already told off transform is converting your normal image space into parameter space. There are different variations of off transform available. In this unit, we are going to study these two types of off transform. First, we see what is standard off transform. After identifying the many edges in the given image, each edge may be the part of the straight line. We need to find what are the group of points that become a straight line. For that, off transform use the parameter space in which the voting can be calculated for each and every pixels. The highest vote can contribute a part of the straight line. Using that peak value, we can identify the straight line. This is the basic idea behind the off transform. These are all the steps for off transform. Let's see one example value. Consider this binary image. These are all the edges identified by the edge detectors. So that coordinate value can be illustrated here. But for off transform calculations, this row by column value can be changed into XY parameter value. So I rewrite these edge pixels by means of XY coordinate value. So this point is represented as 2, 0. So these are all the edge pixel identified by the edge detectors. So in the first step, I identified the edge pixels coordinate values. Then I am going to find the rho and theta value. So this polar equation can be used in off transform. Before going to apply the values, I just illustrate what are the basic degree values like sine and cos theta for 0, 45 and 90 degrees. Let's move to the next step. Now we are going to compute the rho value for each and every pixel. I calculate the rho value for theta equal to 0 degree and theta equal to 45 degree and theta equal to 90 degree. I randomly choose these three values, but in real time we can choose different theta values. So you can include theta equal to 30 degree, 60 degree, 135 degree and so on. For simple calculation, I can choose these 3 degrees only. So you can apply the first pixel for 0 degree, you can get this value, and 45 degree you can get this value, and 90 degree you can get this value. In this way you can identify all the values for different thetas. So in the next slide I can show what are the values calculated for different thetas. Some of the row values are fractional, so I am going to round into the nearest integer. So we are computing the row value for the different thetas. Now we are going to increment the accumulator array. So from this table I can update the accumulator array. Accumulator array is a table that contains how many times the row value can be present for the particular theta value. I explained how this table can be formed from the previous table. This is the previous table. Different row values are illustrated for corresponding theta values. From this value, I can identify the minimum value as well as maximum value. So minimum value here is 0, maximum value is 4. So I can list the row value from 0 to 4. Then for the 0th degree, how many zeros can be present in this column? There is no 0. So I can put 0 here. There is no 1. So I can put 0 here. 2 can be present 5 times. So I can write 5. There is no 3 and 4. So I can put 0 for 3 and 4. In the same way, this column can be updated. For 45 degree, there is no 0. So I can put 0. For 45 degree, only 1 is there. So 1 can be present 1 time. 2 can be present 1 time. 3 can be present 1 time. 4 can be present 2 times. So for this 4, the 45 degree, the value is 2. In the 90 degree, 0, 1, 2, 3, 4, all these value can be happened only 1 time. So all the values for this column becomes 1. So in this method, you can update the accumulator table. So up to this, we are completing this step. Now we are finding the what is the peak value present in the accumulator array. From this accumulator table, so this is the peak value. So the result tells row value 2 and theta value is 0 degree for the straight line. If you are applying this formula, row value is 2, theta value is 0 means this part becomes 0, this part becomes 1. So x is equal to 2. X is equal to 2 is nothing but the equation of this straight line. So in this way, the off transform identify the straight line present in the image. Let's check one more example that contains the noise information. So apart from the exact straight line, we are having some more points. If you are applying the same concept again, you can get the value like this. So here identify the minimum value and the maximum value. So you can list the row value from 0 to 5 and update the accumulator table. Now you can get this value. Here the peak value is 5. So the row value is 2 and theta value is 0. So only these 5 pixels only contribute for this straight line. So we can reject these 2 lines. So the off transform avoid these 2 unnecessary noise and detect only the straight line coordinates. I hope you understand now how the off transform identify the straight line. So the line detection by off transform method is over. Now we are moving to the next topics called foot of normal method. It is another method to identify the straight line. It avoids the trigonometric calculations present in the off transform. These are all the steps followed for the foot of normal method. The main part of this method is called to find the gradients called gx and gy. Then using this, we need to find v value and x0 and y0. This x0 and y0 is called foot of normal. So this coordinate value can tell the exact line equation. Let's see one example. We can take the same example from the previous one. For this image, the xy coordinates are 2, 0 to 2, 4. That is the first step. Next step is to find the gx and gy value. This is the vertical line. I can draw this line here. For this, gx and gy is nothing but gx means the variation in the x coordinate, gy means variation in the y coordinate. For the edge detection method, vertical line has the variation in x coordinate. So these pixels can be vary horizontally by 1. That means 0 and 1 can be changed here. So gx equal to 1. For this vertical line, y value cannot be changed. So gy equal to 0. It can be reversed in the horizontal line. And this is the perpendicular line from the origin to this straight line. We can also find the gx and gy value by one of the straight line formula. So for this image, The edge coordinates are listed here. It starts from 2, 0 and end with 2, 4. First, find the slope using this formula. This value gives 0 in the denominator. That means it is infinitive. So we can conclude this is the vertical line. So the line equation is x is equal to 2. I can rewrite this equation in this format. So 2 can be bring into the left hand side. So x minus 2 equal to 0. So x coordinate value is 1. There is no y coordinate value and the constant value is minus 2. So the coefficient of x coordinate value is called gx. The coefficient of y coordinate value is called gy. So gx is 1, gy is 0. Suppose your line is horizontal line from this image. The starting point is 0, 2 and end point is 4, 2. We can find the slope by using this formula. We can get the value 0. So apply m equal to 0 in this straight line equation. You can get y minus 2 equal to 0. You can compare this equation with this one. There is no x coordinate, y coordinate is 1 and constant value is minus 2. So this one is gx and this one is gy. So for the horizontal line, gx is equal to 0, gy equal to 1. For the positive diagonal line, the starting pixel is 0, 0 and it ends with 4, 4. If you are finding the m value, it becomes 1. You can apply m equal to 1 in the slope point form from the starting point 0, 0. So you can get this value y equal to x. Then you can match with y equal to x with the standard form. So it can be rewritten like this, x minus y equal to 0. So the x coordinate is plus 1, y coordinate is minus 1. There is no constant. So this is gx and this is gy. In the same way, negative diagonal line, the starting point is 4, 0. It ends with 0, 4. The slope is minus 1. You can get y equal to minus x plus 4. We can rewrite this x plus y minus 4 equal to 0. X coordinate is 1, y coordinate is 1, constant is minus 4. So plus 1 is the gx value, plus 1 is the gy value. So in this way you can find the gx and gy value. Let's come to our problem. So we find the gx and gy value from this line equation. So this line equation is a tentative line equation only. After complete the foot normal method only, we will conclude the exact line equation. So up to this we find the gx and gy value. Next we can find the v value by using this formula. So I calculate these values for all the pixels and listed in this table and find the corresponding x0 and y0 value. This x0 and y0 is nothing but foot normal value. So for all these pixels gives the same value, that is called 2, 0. So we will conclude these 5 pixels having the same foot normal value 2, 0. Then final step is we can convert it into the original format. So we can convert this foot of normal method into original form. So now the equation is x equal to 2. So this is the confirmed line equation for the given image. But sometimes the questions can be asked by giving the line equation directly and give one of the edge point to calculate the foot of normal coordinate. You just compare the previous example. In this example, we listed all possible coordinate value and identify the tentative line equation. But in this problem, the tentative line equation is directly given. For previous example, we calculate these values for all these pixels. But in this example, only one pixel is given. So we can do the calculation for these pixels. So first you identify gx and gy value. Gx is plus 2, gy is 1. Then you find the v value. Next you find the x0 and y0. So in this problem, x0 is nothing but 16 by 5, y0 is nothing but 8 by 5. So finally you find the foot of normal coordinate value is nothing but 16 by 5, 8 by 5. It is also written as 3.2, 1.6. So after this foot of normal method is over, let's move to the next topic called line localization. These two concepts give the exact line equation only. These two methods tells how the line is flows and how the line is exactly fit in the xy plane. And the best example for line fitting is Randsack line fitting. So we will see this one by one. So the line localization tells where the line lies in the original image and what are the pixels belong to that line. This information can be derived from either off transform or foot of normal method. In our examples, we are discussing only simple images, but in real-time images having more number of coordinate values, it is very hard to identify the straight line. For that, we need this line localization and line fitting. Now we can derive the hierarchy of these concepts. Using the edge detection that can be discussed in the previous units that tells the coordinate pixels present in the image. Using that we can identify the straight line either using off transform or foot of normal method. Then line localization tells how exactly the lines in the xy plane. So let's see one example using the off transform method and finally tells the identification of the line. Let's see this image. The coordinate points are illustrated here in the xy plane. Then find the row for the different theta values. That can be illustrated here. Then update the accumulator array. Here -3 is the minimum value and 4 is the maximum value. So I can start from -3 into 4 for the row column. Then count the values and update the accumulator array. Then identify the peak value. So it tells rho equal to 3 and theta equal to 45 degree. If you are applying these value into this polar equation, you can get the value like this. So finally you can conclude all these 5 values are contribute the straight line. So using line localization you can identify this is the starting point and this is the end point and what are the pixels are contributed for this line. Then finally you can draw this straight line using this line fitting. So the line fittings comes after the line localization and draw the exact line. And this is the hierarchy of this concept. Line detection is our goal. The edges can be calculated from different edge detection mechanisms. The line equations can be identified by either off transform or foot of normal method. Then that equation can be mapped with the xy plane and finally that line can be drawn using line fitting mechanism. And RANSAC is the one of the best robust line fitting mechanism. So that can be discussed in the next part. So this RANSAC method having the repeated mechanism to identify the best fit of the line. For our examples, for the simplification purpose, we are handling only the simple images like this. But in real time, there are so many pixels are there which leads to confuse to produce the actual straight line. So we need the best line fitting mechanism. These are all the steps for RANSAC line fitting mechanism. The basic concept is we are taking any 2 points randomly and draw the imaginary line. That line is called candidate line or hypothesis and check how many remaining points close to this straight line. This process can be repeated n number of times. So in the next step, another 2 line can be taken and the candidate line is drawn. Then identify the remaining pixels how close to that line. After all iterations, we can list out all the values, find the peak values. From that, we can identify the best fit of line. The number of iterations can be depends on number of edge pixels available in the image. Suppose the total number of edge pixels is 10. This is the formula for maximum iteration. 10 into 9, 90, 90 divided by 2, 45. So this process can be iterate maximum 45 number of times. Let's see one example. So I can take this image with the noise information. So in the first step, I can listed the edge coordinate values. I can rewritten in the xy coordinate values. So first I pick the 2 random points. For this image, I can pick these 2 pixels first. So the coordinate value is 2, 0 and the second pixel coordinate value is 2, 4. And then I can find the candidate line. From these 2 points, I can find the line equation. Here the slope value becomes infinitive. So the line equation is nothing but x equal to this x coordinate value is 2. So x equal to 2. The next step is find the distance between this line from other pixels. So I can list out all the edge pixels here and the equation is x is equal to 2. That is nothing but x minus 2 equal to 0. So I can find the distance for this formula x minus 2. So x is this x coordinate value, minus 2 is the constant value. So 2 minus 2 becomes 0. Here 2 minus 2 becomes 0. Here x value is 4, that is this point. So 4 minus 2 is becomes 2. So this is not satisfied for this line. So this pixel is treated as outlier. So in this way all the calculations are made. So this is called the distance value. If the value 0 means these pixels are lies in this straight line and the value 2 tells these pixels can be away from 2 pixels. So this value tells the distance from each pixel. So if the distance is 0, you can take that pixels only. So these 5 pixels only taken for the straight line. So up to this we are calculating for only 2 pixels. So this process can be repeated n number of times. In our example, n value is 7. So 21 times this process can be repeated for different starting pixel and end pixel. So I can choose the another two values, that is 2, 0 and 4, 3. These two values. So I can draw the candidate line and identify the line equation from this starting point and this end point. The slope is becomes 1.5 and the line equation becomes y equal to 1.5x minus 3. The next step is calculate the distance between other pixels. So I list out all the pixels here. I can get the line equation like this. So I put the actual y value. So these y coordinate values can be listed here. Then apply these y value from this equation, that value listed here. Then compare these two values and find the difference in this column. If the difference is 0, that pixel is belong to this line. Otherwise, that pixels is not part of the straight line. So in this case, there are 2 inlayers are there. But in previous case, we are having 5 inlayers. So in this way, number of inlayers can be calculated for the next iteration. In next iteration, the next points may be this and this or this and this. So up to 21 number of times this process can be iterated. So that total number of inlayers can be tabulated here. So for this starting point and end point, we can get 2 inlayers. For this starting point and this end point, that is this one and this one, we can get 5 inlayers. So in this way, all the 21 combination of 2 points can be listed here and the total number of inlayers count can be listed here, from which the peak value can be identified. So it tells these 2 pixels, that is this one to this one, is the best straight line. Finally, that pixels can be drawn as a straight line. So this is the method to fit the line by using ransack method. So up to this we are completed the line detection. Moving to the circular object detection. So Hopf transform is not only detect the straight lines, it also identify the circular shapes. When it is used for circular object detection, it is called circular Hopf transform. As usual, the Hopf transform use the parameter space to identify the circles. This is the circle equation. Here A and B are the center of the circle. R is the radius. These are all the steps followed by detecting the circular objects in the image. Let's see this by one example. This is the pixels given in the image. We need to identify the circle in the image. So before calculation, we can take the radius value. The radius value is also given in the question. Sometimes the radius value is not given. If the radius value is not given or not known, you can assume the radius value for further calculation. So in this example, this is the center point and the radius can be 2 units. So I can take r equal to 2. So this is for manual calculation only, randomly assign the value. So these are all the available pixels in which these are all the edges are identified by the edge detection method. So the next step is to set up the accumulator. So accumulator is the array. Initially it has 0 for all the values. The next step is to identify the possible centers. For this, you can take the first pixel. First pixel is nothing but 0, 2. Here we are using row column value for the pixel coordinate, not xy coordinate. So the first pixel is 0, 2. That can be applied to this equation. For this pixel value, the equation looks like this. Now you can use this equation for all the pixels available as the edges. So I can list all the edges here and apply this value to this equation and calculate the result. If the result is 4, that means same as this value. This is the valid center. So for these pixels, I can identify 3 valid centers. So 0, 0 is nothing but this one, 0, 4 is nothing but this one, or 2, 2. So these are exactly differ from the radius 2. The meaning is for these pixels, any one of these 3 act as the actual center. So the valid centers are 3. So I can update the accumulator value into 1. I can show this accumulator visually. Initially your accumulator having the 0 values for all the coordinates. For this first edge, we are finding the 3 possible centers. So first one is 0, 0. So 0, 0, this value becomes 1. Then 0, 4. 0, 4 is this point. So it becomes 1. Then 2, 2. So these three values are updated in the accumulator array. Then we can move to the next pixel. So I can take 1, 1. So this operation can be iterated for all the edges. Then update the accumulator value. From this, find the maximum value. So these are all the steps given in the circular object deduction. So after updating all the pixels, your accumulator array may looks like this. And this one is the peak value. So we can easily tell 2, 2 is the center of this circle present in the given image. That can be written as the result like this. So in this way the circular object can be detected. Let's we move to the next topic called accurate center location. So in the circular deduction, we are mainly identify the center of the circle. In real-time images, it is very difficult to identify the center of the circle. So we have to add some extra mechanism to find the accurate center location. And this is one of the method. Take any one of the edge pixel, draw the straight line, write the perpendicular line towards the circle. In this way, take another edge pixel, draw the straight line and draw the 90-degree line towards the circle. In this way, you can repeat all the edges. We can check this intersect point, how many lines are intersect to this point. If you draw this line from all the exact edges, we can get more count. Suppose the pixels belongs to the out of this circular edge that may be present here or here. If you are drawing the straight line like this towards the circle, it does not intersect this point. So the more number of intersection tells this is the center of the circle. Let's move to the next topic called speed problem. Speed problem is nothing but the execution time is more when more number of edge pixels are identified. This issue is called speed problem. To solve this, we are using different mechanisms for off transform method to become faster. The next topic is called ellipse deduction. Ellipse is nothing but elongated circle. It has two radius. One is major axis, another one is minor axis. Major axis represented as A, minor axis represented as B. This is the equation of ellipse. In circle deduction, we are going to identify the center of the circle. In the same way, ellipse deduction includes identify the center of the ellipse and major and minor axis value, that is two radius values, and how this ellipse can be tilted in the xy plane. If you are taking circle and ellipse, if you are rotating the circle and ellipse in same angle, it maybe looks like this. So circle does not change. That's why we are having the one more parameter for ellipse deduction. This ellipse deduction is somewhat difficult to compare circle deduction because it consists more number of parameters. For this computation becomes slow, it leads speed problem. These are the two methods to achieve the ellipse deduction. First one is diameter bisection method. In this method, 2 points can be taken opposite to the ellipse boundary and calculated the different votes. From the maximum vote, we can identify the center of the ellipse. But this method cannot be suitable for all the situations. If ellipse can be overlapped to one another, it is difficult to identify the center. That's why we are moving to the next method called chord tangent method. Here, the two tangents can be drawn. First, we take two random pixels around this ellipse boundary. In this example, I can take this one and this one. You can take any 2 points in the ellipse boundary. Then you can connect the P1 and P2 as the straight line. Then you can find the midpoint of this straight line. The P1 coordinates are called xi and yi. P2 coordinates are called xj and yj. So this is the formula for finding the midpoint of this straight line. Then you can draw the 90-degree line towards the ellipse boundary. So this point is called K. You can extend this point into the opposite direction. Then draw the two straight lines that can be meet into this line. So these two lines is called, that is TP1 and TP2. These two lines are called tangent of these lines. So these tangents gives the some more extra parameters value to give more detail about the ellipse center. So it can be applicable for most of the real-time situations. So up to this circular object detection part is over. Next we move to the case studies. For applying these concepts, we can achieve some real-time examples that can be illustrated as the case studies. I can give the clear notes in the description section for these case studies. You can read that content. If you have any doubt, you can make the comment. I am happy to answer your comments. Don't forget to download the notes present in the description part, and thank you for learning with me.